Thank you for the introduction. It's a real pleasure to be here. I wanted to start off really thanking Matt Tivnan, who is the senior PhD student who's working on this. He's really led the effort. And to be clear, this is his work and I'm presenting on his behalf. I'd also like to thank all of my other colleagues, both Johns Hopkins and collaborators and sources of funding. So I am talking about deep learning in the CT imaging chain. I think when you look at what's happening out in the world right now, it's that's often applied as denoising of low-dose CT data. It's wildly popular as a research area, and there are a gazillion different techniques out there across neural network architectures, loss functions, training methodologies, et cetera. And as I kind of look out there, if you look at the ensemble of most of that work that's out there, you're looking to find kind of whatever that best image is, the thing that minimizes RMSE or PSNR. I think that's great, but we do have to be careful. We know that for different imaging tasks, different images provide you different information. So there's, of course, growing interest in task-based performance for these kinds of neural network restored images. I think it's also important to note that when you restore images using neural networks like this, the image properties that are output from them are complex, and what properties they have is really based on the inferences they've made based on the data you've given it. So what kinds of blur have gone in there? What does it mean to have an artifact, or what is noise? So I want to get image quality models back kind of into the equation here. They're often used in assessments, things like modulation transfer function and noise power. Now, those are pretty tricky to apply to neural networks because of the nonlinear processing. So maybe there's other things we can do where we do some more exhaustive simulations or even look at things like posterior sampling. The last time I was given the opportunity to talk here at a Deep Recon meeting, I also presented Matt's work, where we looked at a new kind of loss function where you can actually separate the kind of two pieces of the output. So mean squared error is comprised of both the noise and these kind of bias terms. We're able to separate that by explicitly training, giving it large ensembles of noise realizations. Then you can calculate sample means and sample variances. That lets you kind of customize anywhere on that spectrum of image quality. So I want to think about other ways we can do this kind of thing. And the tool that I want to discuss are these denoising diffusion probabilistic models. If you haven't seen them before, the way they work is you define a temporal process by which the image is degraded. Now, this may not be actually what's happening physically, but I'll discuss why you might want to do this mathematically in a second. But you start with the kind of ground truth image at time point 0, and you incrementally add noise and kind of fade the image away. And there's a movie of that forward stochastic process here. And you can, of course, at any given time point, you could write down what is that image x of n along that temporal sequence. What you can do is you can design a neural network to try to estimate that noise term here at any time point in the sequence. And you generally do that by giving it lots of different time points, it gives you the time value itself, but you also condition this based on the data itself. So it knows kind of what that background is, and it can figure out what the noise is. And what you're able to do then is to define a reverse stochastic process where you kind of incrementally subtract out that noise. And this is a movie of that reverse process happening here. And you can dig into all the math in more detail, but what I like about that is this is a way of making really kind of a very deep network that actually has a relatively low parameterization, because you're only looking at that kind of incremental effect. The other nice thing about it is because you start with noise, you can run this many, many times. And in fact, the process itself is stochastic, and you can look at these kinds of posterior samples. These are all images that may be equally representative of what's happening kind of under the hood. So that kind of model has been generalized, really thanks to Young Sung and team. so that you don't have just necessarily a scalar fading function and an increase in noise. You can write down a more general reverse stochastic process if you adopt this forward model. And in general, what you find out is that there's this key term in here called the score, which is based on the probability of those interval kind of time points. And that's the thing that you're actually trying to estimate with a neural network. If you can do that, then you can develop this reverse stochastic process. So just to show another example of this, let's define an arbitrary temporal sequence where the image is fading according to this, this term M of t, and the noise is increasing according to this V of t. You can write down that stochastic differential equation. You can write down the score. Again, that's the thing you're going to be training your network on, but the way you apply it is through this reverse stochastic differential equation. And in practice, you're going to do that with a discretized version. And the original DDPM that I showed you before is really a special case where there's just a single scalar defining both. So just to illustrate what this looks like, let me start with this ground truth and define this kind of fading term as a decaying exponential. The noise is coming up quadratically. You can see that forward stochastic process here. Equivalently, you can start with noise and run the reverse stochastic process. And this again is conditioned on the data that we've observed, so that we're going to get to a sample of this ground truth. And here are posterior samples that you might look at, and based on maybe many of these, you decide what features are important, what are not. So the generalization that I'd like to look at is, can we change this so that we have an image quality model that kind of reflects our imaging system? So instead of having a simple fading term, what if the incremental thing that's happening to my image in terms of degradation is some amount of blur? In fact, let's keep it simple. It's just a little incremental shift invariant blur. And moreover, let's have additive noise in there, but maybe it's not white additive noise. Maybe it's the kind of noise that I see in CT or whatever imaging modality you're working with. You can then again, there are just 4 time points here, or 5, that you can go through that same kind of modeling sequence. You have that probability chain defined both for the forward process and the reverse process. And what we're going to do is, in that reverse process, instead of having that conditioned on the ground truth, we'll have it conditioned on the actual measurement data, so we can actually apply it to measurement data. So in this case, I can write down a new set of forward stochastic processes where I have a time varying MTF. So my image is going to degrade in a very specific way in terms of modulation transfer function, and the noise is going to come up in an analogous, very specific way. You can apply this using Fourier transforms. We have the same kind of forward model here. Here again is that score term that we're going to estimate using a neural network. And the continuous reverse stochastic differential equation and the discrete version, which we're actually going to use for our restorations. I haven't told you how we've done any of this yet, but we're going to use a fairly standard network that is going to be trained with an ensemble of all kinds of degraded images at different time points. So these X of T's. We're going to give it the measurements themselves as well, so it can tell the difference between noise and the background image. But it also needs to know the time point itself. And in fact, the one thing that is a mild permutation on a standard model is we're going to allow this time point to go into a kind of a fully connected layer. We found that that helps a lot with training. So let's take a look at what these look like for a temporal process where the MTF and noise power are both defined in terms of 3 filters: a low pass filter, a band pass filter, and a high pass filter, all based on kind of simple arithmetic of a Gaussian low pass filter. What we can see then is you see that forward process. We start with a ground truth, but instead of evolving to pure noise, we're evolving to something that has the kind of chunky, blurry image that we expect in some CT scans. And you can analogously then run the reverse stochastic process and see what that looks like, and moving back towards ground truth. And equivalent, we can still look at these posterior samples, which we think are perhaps a good way to talk about image quality. Now, I want to go one step further. In that previous example, I didn't necessarily match that time equals, so I'm going from the time point of 0 to time point equals 1. That last time point, I can force that image quality, that noise power and MTF to be exactly what I find in my data. What that allows me to do then is to use the data as an input to that reverse stochastic process. So if I stop this here, I'm right at the end of the sequence. You can see that that forward model and the measurements, they're not the same. They're different noise realizations, but they have a similar image quality and character there. So then I can start with my measurement model here, run that reverse stochastic process, and by the time I get to the end, I'm more in the regime of where I am with my ground truth. Now, something I'm generally interested in, we won't talk about much here today, is perhaps I'd like to stop somewhere before I get to ground truth, because I think hallucinations might kick in or other effects, or maybe there's simply a better balance of noise power and MTF for the task that I have to be looking at. And of course, you can look at these kinds of posterior samples that I'm showing here. So we've done this. I think a natural question that follows right from this is, well, what's the difference between this kind of what we're calling a Fourier diffusion model and the original scalar models that are widely applied? So as a reminder, the original scalar model is starting at t equals 0. The image fades. White Gaussian noise comes up to t equals 1. Our Fourier diffusion model, we start again at the ground truth, but that end image is an image of the kind of image quality that we expect from our CT scanner. Again, I don't need to go into the details here. We can talk about it more if you want, but here's some details on how we do get our data. It's from the LADC data set, some of the training numbers. More importantly, in the evaluation, I want to look at a comparison between these methods of the mean squared error, the mean squared bias, and variance. And the other thing I'd like to look at specifically is the performance versus the number of time steps. While these diffusion models are really powerful, one of the drawbacks is if you need many time steps to apply them, they're computationally complex. And again, just to kind of move the point home, in the scalar model, you're starting, if you're just fading the entire image, that means all frequencies are disappearing equivalently. We're starting at the top, moving down, whereas the measurement data has a frequency distribution of a certain form. Same thing for the noise power. The noise power is coming up uniformly, even though if you're doing FBP reconstructed CT data, you tend to get this kind of mid-frequency donut in your data. In contrast, the Fourier model starts with that uniform MTF, comes down to what you see in the data, and same thing happens in opposite with the noise, up to that mid-frequency donut. So if we look at the scalar diffusion model, showing a sampling of 1,024 time steps as we go from the truth to the noise image, the reverse process goes this way. We can see there's good matching between those time steps in the forward and reverse. I'm going to stick with this, but now, even though we're operating the full image, it's helpful to look at the zoomed in version. If I go to the Fourier diffusion model, you can see that I start there and with the blurred noisy image here. We run the reverse process. Looks good. We have similar image properties. They're not the same image because there's a different noise realization there. What we see if I reduce this radically to 16 time steps with the scalar diffusion model, there's no longer a good match between the forward and reverse process. In fact, if you try to get all the way back to time 0, it's not a particularly good restoration. Whereas with the Fourier diffusion model, I think you could argue that it does look good. To put some quantitation on that, they look at the summary performance here in terms of mean squared error versus the number of time steps. You can see that the Fourier diffusion model holds on as you go to smaller numbers of steps, but also performs better across the board in terms of mean squared error, mean squared bias, and mean variance. And that is all I really want to talk about today, but to quickly summarize, these Fourier diffusion methods allow for explicit modeling of the image properties that we have in CT. And this is something we know we've modeled for a long time. I think they're interesting that they allow for early stopping, that we can stop before we kind of over denoise. That's not fully investigated. They appear to require fewer time steps than scalar DDDPMs and show improved performance. I think there are a lot of unanswered questions here on exactly what we want that temporal evolution to be. How do we integrate this within task-based performance analysis? And how do we apply it to the more complicated features of CT, which is the image properties can be shift variant, and maybe we don't want one distinct MTF and noise power. This is the archive paper that Matt wrote, just went online at 1 a.m. this morning, so you can look at the details at your leisure. Thank you so much. Questions?
Very interesting work. I'm curious that once you apply a filter, then after several steps, your noise becomes correlated. When you have more steps, it's more correlated. Then theoretically, the current way to calculate the score function to accelerate this computation doesn't work in a way, because it's required that is IID noise in your image. So did you see anything any artifact or anything caused by this? I know it works, that's what matters. I'm just curious whether you see some artifact or something caused by this.
We haven't seen any artifacts, and of course, I would love to speak more to the details of Matt's work, but I believe in his derivation in this paper, he's got the math kind of written down for the correlated noise aspect. So I think we're still matched in terms of that reverse stochastic process.
Okay, so I think it's an excellent work. You mentioned early stop. Do you think you keep going, you will combine denoising and deep learning together?
I think we are already, even if you stop early. It's so this is something I didn't show much, but the other thing Matt has looked at is in those intermediate steps, how well do we match in noise power and MTF? And this gets back to this kind of idea of how do we define that temporal trajectory? Are there interesting intermediate time points that we can actually specify and stop there because we think they're good for specific tasks?
Second question, your time variable goes through a fully connected network. Would you please explain a little bit further?
So I don't know how much intuition I have on this, but I think depending on what your temporal evolution of these properties are, it seems to, by giving it that kind of fully connected layer, it's allowing a nonlinear kind of transformation of that time point that it just seems to train better. I don't have a lot of intuition or
I think that's your intuition. I would agree with you. It's a nice idea. Okay.
Good. So nice work, Webb. Okay. Number one is really simple and quick question. So did you apply the trend network to any of your experimental data from?
No, we haven't done that yet. This is pretty hot off the press. Matt's been looking at applying this to some real data, but we don't have any ready for public consumption.
Yeah, the second one, a little bit technical. So when you take into account the MTF and MTF inverse into that, I really like that idea. Essentially try to do the deconvolution, try to deblur the image. So when you do that, and the stochastic differential equation actually does not give you the statistical distribution to help that. But the Jonathan Hall's the diffusion probabilistic model use local change of the Gaussian distribution. That one might work. So I would perhaps suggest you to separate the deblur from denoising, you just look at the deep blur and using Jonathan Hall's method, because locally you change the Gaussian distribution. That is doable because anything you have is just anything you can just approximate as a Gaussian at local local position. That may help to deep blur to make it explicit and work very well.
Well, thank you, Guanghang. We'll look into that.
Thank you.